We have defined surface tension in terms of energy and work done as, if you remember, surface tension is the amount of the work done in producing a unit change in the surface area of the liquid. From this, we have done that in the previous video. You can please look into the previous video if you're not familiar. We can calculate work done as surface tension into change in the area. Taking this concept into consideration, if somebody has asked you a question, the question is like this. A water drop a radius is increased from R1 to R2, where R2 is greater than R1. What is the work done if somebody's question is that? I can use this formula. Work done is equal to T into delta A. Delta A is final area minus initial area. Being the drop is spherical in shape, its surface area is 4 pi r square. So T of 4 pi r2 square minus 4 pi r1 square. That's the answer for the question. You can substitute the data, whatever is given for you, and just solve the problem. If suppose the question is slightly different, if suppose someone has asked you a question like, if a soap bubble, it's not a water drop, be careful. Earlier it is a water drop. Now I'm talking about a soap bubble is blown such that radius changes from R1 to R2. How a soap bubble is different from a water drop? So this is a water drop. Its inside is full of water itself. So its surface is free surface is only the outer surface that is free. But if you look at a soap bubble, it is like this. Inside the soap bubble, it is empty. So what happens? The free surface is there inside as well as outside. Assuming it has a very small thickness, inner surface is having a area 4 pi r square, outer surface will be having another 4 pi r square, therefore the total free surface will be 8 pi r square. So in that case, the formula for the work done will be T of higher area minus smaller area, 8 pi r2 square minus 8 pi r1 square. I want you to understand little carefully why I have written 8 here and why I have written 4 here. Yes, the logic is very simple. Here inside it is filled with water. Here inside it is empty. Therefore, in the case of a soap bubble, there are two free surfaces, both inner and outer. Whereas in the case of the water drop, there is only outer surface is free, but inner surface is filled with water, and that's not a free surface. That's how we have to solve this kind of small problems. I've just done this as a kind of a preparation for the next concept that we are handling. The next concept I'll be talking about what happens when a big drop splits up into identical drops. What's the work done? I would like to do that in the next video so that this basic concept works like a preparation for that. That's it. Thank you for watching.